So good afternoon. Let's start today's workshop, and this is the landing GitHub page for the Data Lab workshops. uva-datalab.github.io, and we go into the Introduction to Classical Machine Learning notes, and inside today we will be talking about clustering algorithms. So we go there. Okay, this is another case of unsupervised machine learning, and we will review a few sets of different clustering algorithms. Again, when we are working with classical machine learning, our basic library is scikit-learn from Python. So this library allows us to do different types of tasks like classification, regression, clustering, dimensionality reduction, model selection, pre-processing. And we have done a few of these topics, and we will continue covering most of the libraries by type inside scikit-learn. Okay, so let's go back to the notes. And there are several algorithms that I want to address. The first one is called k-means. It's not exactly like k-neighbors algorithm, but this also has to do with when you have a set of data or data set, and you want to know how to group this data into different clusters, and the different clusters will have their own center of mass, let's say, or center of gravity. And we are looking for a specific way of separating the different clusters and trying to optimize some difference or distance to the center of the group. So that's k-means. And we need to say initially how many clusters we want to explore for a specific data set, and then we have to use different metrics to see if our initial guess can be validated. So we will have a set of metrics that tell us. The next algorithm is called mean shift, and this is similar to k-means, but we don't have to specify how many clusters we want. Everything will be handled by the algorithm. Okay, and it will work in a similar way. There's another type of clustering called hierarchical clustering, and what we do is create these dendrograms, and it will organize the data set into different clusters, and every cluster will have different elements of the data set. We will be seeing, in short, the Jupyter notebook that where we can do this exercise for reviewing the different types of algorithms. Another algorithm is called dbScan, and also the idea is just to cluster the different data with similar properties, and this algorithm is used basically to detect outliers or apply it to some anomaly detection or fraud detection. So it's called dbScan. And another one which is similar to dbScan is the algorithm optics. And there we handle some parameter to test different options, and we will get from this algorithm reachability plot, and it will tell us how many clusters we need. In this case, we are seeing 5 sets of data, so we will have 5 different types of clusters. And then if we are having like images, then we can do spectral clustering. It has to do with eigenvectors and eigenvalues. And so this is used basically in image segmentation and object recognition. We are not going to see any example of that today. And then there's another one, which is called the Gaussian mixture models, also to estimate different clustering, also applied in image segmentation, speech recognition, and some other applications. And lastly, we have BIRCH, which is another clustering algorithm that can be applied to large data sets. Okay. Of course, if you go inside the scikit-learn, you will find there are many different types of algorithms you can apply for clustering. And these are the different, the comparison between the different algorithms, okay? So you have several options to try. And then, as always, when you're doing some data analysis, it's good to have 2 or 3 options and then compare what gives you the best results. And so you can justify your assertions or your hypotheses. Okay, let's go back. Okay, please tell me when you have any questions. This is the way you will be importing the different algorithms from scikit-learn. So we have k-means from scikit-learn cluster, the same as mean shift and spectral clustering. And then we have dbscan from the cluster, and then from the mixture library, we have the Gaussian mixture, and everything else is just the cluster library from scikit-learn. Okay, so now we can jump to the examples of the Jupyter Notebook. So let's do that. And it will open a GitHub image of the Jupyter Notebook, and then using your Gmail account, you can open this notebook in Colab. Okay. So let's do that. And we're going to be analyzing a specific data set, and we're going to be testing the different algorithms. In our case, we'll be using the famous penguins data set. So let's run the first cell. I'm going to import all the necessary libraries into the memory of Google Colab. So NumPy, numerical Python, scientific Py for some numerical algorithms, pandas for doing data analysis and cleanup, matplotlib, pyplot for doing visualization, and Seaborn, also another visualization library from Python based on matplotlib for doing visualization. And we import these other libraries to filter out some warnings and ignore them. Okay, so we run it, yes. And then we wait for the green check mark. Okay, so it's done. And then we're going to read the penguins data set from this GitHub repo. We're going to be using the function read CSV from pandas. And then let's do that. Okay, and then we print the first 5 rows of the penguins using the function head. Penguins is the name of the data frame. So this is how it looks. So we have the species of penguins, which are 3 types, the 3 types of islands, and then we have some measurements: culmen length, culmen depth, the flipper length, the body mass, some in millimeters, some in grams, and also the gender. And then I found this interesting from Google Colab. If you have a data set, you can view the recommended plots. Let's try that one and see if you have a data set and you read it to Google Colab, it will generate possible types of plots that you can explore, like do the basic exploratory data analysis from a data set. So everything now is integrated. The AI algorithms are integrated into Google Colab. And now Google has Gemini, which is the substitution of BART. So now it's generating the different types of plots. You don't have to code anything. Then you can see the different histograms for the different numerical variables, and also you can see the box plots, not box plot, like histograms for the categorical variables. Then you can do the scatter plots. You can have different heat maps and violin plots for the different species. So for example, we can see species versus, you can see the species in a violin plot, the variable culmin depth, and also you can see the code it was used to generate. So it's a very good learning experience. You just need to upload the data set into your Google Colab session, and then it will help you to create the basic plots, and it will give you the code to explore those plots. So most of the work is going to be facilitated by AI. Okay, so we continue. Thank you for the plots, but we continue and using pandas. So we use the function info from pandas to see the basic information from the data frame. So we have 344 entries. We have 7 columns. This is the distribution, and you can see that not all the columns have the same number of rows, non-empty rows. And then we have to drop the rows that have missing values. And also in this case, for this specific penguins data set, the sex from one of the rows, it's equal to dot. So I will just select all the rows from the penguins data set that is not equal to dot. So I just have the male and female options, and then I do that. And now I have only 333 entries on all the different columns. And this is the type of data. So species and island are categorical variables, the same as sex or the gender, and numerical are floating 64 bits, all the measurements from the different penguins. Okay. Then we can do a basic scatter plot using Seaborn function per plot. And so we're going to use the dataset penguins, and we're going to use species, the variable species for the color. And then we create the per plot, and we define some size. Okay, so now we have the variation of each variable versus another. And in the case of the same variable, we have the kernel density estimate. And in colors, we have the different types of species, the Adelie, the Shinstrap, and the Gentoo. And on the matrix, we have, for example, body mass versus culmin length, or body mass versus flipper length, or flipper length versus body mass, etc. So you can see if there is a relationship between the different variables. Okay. And then I'm going to exclude the species from the data frame. So I'm going to, my data frame has species, island, culmin length, etc. So I'm going to exclude the species, and then I'm going to try to create clusters for the data set without telling what species they are, so the algorithm can try to determine some clustering. Okay. That's the purpose of this one. Okay. And so I will create my Y variable, it's just the species, and penguins main, it's just the penguins data set without the species. And then I'm going to create these artificial variables for the categorical variables. So the categorical variables are, for example, the island and the gender. So it will create, for example, for the penguins living in the island Torgensen, they will give you 1 and 0 the other values. And for penguins living on a different island, you will just have 1 on that specific island and 0 otherwise. The same for the gender. It will be male, 0, 1, or female, 1, 0. And that's the only options. So that's the encoding part, get dummies. It's important when you have numerical and categorical variables to all the main algorithms in machine learning. They're very good working with numbers, and they don't know how to work with categorical variables. So you have to convert or encode the categorical variables into numerical. And there are several ways of doing it, and the best one is using the get dummies. If you just do like a label encoder, like if you have gender, you only have 2 genders, then one gender will be value 0 and the other one will be value 1, but then the algorithm will think that the one that has 1 has more importance or relevance with respect to the other one. So it's good to just use get dummies and the library, and then just convert to zeros and ones. And if it's a binary, 0, 1, and if it has 3 values, 0, 0, 1, or 1, 0, 0, etc. So that's the get dummies function from pandas. Okay. So now we have 333 rows, and then we are going to apply k-means algorithm. So this will be our first classification. And depending on what are your basic variables, you will have specific cluster for that collection of data or columns. So in this case, I'm going to fit. So if I want to make clusters in the penguins, I'm not a penguins expert, but I think that the relationship or ratio between culmen depth and culmen length must be specific to each species. I don't know that. I'm just guessing. Or I could try some other combination. I could try maybe flipper length versus mass, and then I will get a completely different clustering answer. So let's try these first two. And so I'm going to use k-means from the scikit-learn cluster library. I'm going to propose initially 3 clusters, and I'm going to, for reproducibility, I'm going to start my random state at 42. Then I'm going to fit this model. The model is named k-means here. So I'm going to fit k-means for the specific 2 columns of x, the culmen depth and the culmen length, and execute and wait for the green check mark. Okay, so now I have my model fit to my specific data. Then I'm going to extract the k-means labels and create a new column called k-mean labels for x. And after that, I will plot. So I'm using Seaborn I'm going to use the style white grid. That's a white with grids. I'm going to use a color palette called Deep. I'm going to scale the fonts. I'm defining, setting the figure size. Then I'm going to use a scatter plot from Seaborn for the data X and just select the X Kuhlmann length and Y Kuhlmann depth. And I'm going to use the k-mean labels that we just got back from the k-means as colors to distinguish between the different clusters. And I'm adding the title, Y label, and X label, font size, and then show the plot. So this is how does the Kuhlmann depth versus Kuhlmann length for the three types of species. And I said initially, give me 3 clusters. I could say organize it in 6 clusters or 5 clusters. So how can you know which number of clusters is the appropriate one? The answer?
Quickly, we have a quick question chat.
Okay. K-means will be really powerful for features that you already suspect are related. As I told you, I'm not an expert in penguins. So I can imagine what's a penguin, and if I see at the different peaks for the Kuhlmann length and Kuhlmann depth, I guess that property is specific to every species of penguins, right? And remember, in our data set, we have about 333 specimens of penguins, and I have some distribution between the 3 types of species. So I guess that the peak is characteristic property of the penguin species. We will see that I will select other variables and see, for example, maybe I can cluster the penguins by their flipper length and body mass, but then I will have different clusters, because maybe depending if the penguins are more adults and weight more, or some species weights more than other. So you have to play. There's no single answer, and then you are analyzing the different properties of the penguins. Okay. All right. So how can we define how many clusters are needed? And then we have this method. It's called the elbow method. The elbow method will try to compute some difference, and we will create a plot, and let's just execute this part. So I'm going to do the k-means for this X I defined, and try a range of clusters from 1 to 8. And then I'm going to, for every different cluster structure, I will take the average distance within each element and the center of mass for that cluster. And then I'm going to plot. So I'm using the clusters, and I'm going to fit X, which is the Kuhlmann depth, and Kuhlmann length. And then I'm going to take the average distance, and then I'm going to plot using, and this is the plot I get. So this is called the elbow method. So if I using one cluster, I have very large distance because the data set is just spread out. If I use 2 clusters, this is my average distance. If I use 3 clusters, this is the average distance between the elements of cluster and the center of mass of the cluster. And you can see if I continue increasing the number of clusters, the distance is every time less and less. So a good indicator of the number of clusters you should try, it will be, you have this curve and it looks like a arm, and this is the elbow, right? So it can be 2, can be 3, or can be 4, but this is the elbow. Okay, so we are still not sure if good is good or 3 or 4. But not 1, and maybe it's too much, 5 or 6. So this is the elbow. Okay, this method is not very reliable, as you see. So there must be another way of doing that. And another way of doing it is called the silhouette method. And the silhouette method will just do again compute the separation distance between the different elements of different clusters, and we will make a plot. So without going into too much details, I'm going to use the k-means, and also I'm going to use the silhouette score. It's going to be an average distance. I'm going to use the visualization libraries and NumPy, and I'm going to be using the Kuhlmann length and the Kuhlmann depth values. And then I will create range clusters from 2 to 6, since that's my indication from the elbow method. And then just execute. And it will create some plots, and we will go into detail. Okay, so now we have this result. We don't have to understand everything. We just need to look at the plot it creates. So let me go up here. And I have the silhouette score for each. If I have only 2 clusters, this is my silhouette score. For 3 clusters, etc. And you can see that the silhouette score is diminishing. So our best bet will be, again, between 2 and 3 clusters. Sometimes, depending on your data set, maybe you have a silhouette score that has a maximum in between, so that will be your indication of your best bet for the number of clusters. So in this case, it's just a descending series, so the larger the silhouette score, the better. So again, I'm going to be playing between 2 and 3. Okay, so let's look at the silhouette plots for 2 and 3 clusters. So let me move this up. Okay, so what are we looking for? So this is how the Kuhlmann depth and Kuhlmann length will cluster. These are the first cluster, and this is the second cluster. And then this is the silhouette score, and this is the red dotted line. It's just the silhouette score average, or average silhouette score. And then the green one will be the distance, the average distance between each of the elements of the cluster, the first cluster, to the center of mass. And this is the second one. So you can see that these two, I will say, blobs have almost the same width and almost the same height. So that will be a good indicator that maybe only 2 clusters is enough, okay? But we have 3 now, so we can see how the silhouette for 3 clusters looks like. Again, almost uniform, but almost the same height. We have a little less silhouette score, and you can say that in a good approximation, the 3 clusters have almost the same properties, except that this one is a little bit larger, but that's okay. And this is how we would look at the 3 clusters. Let's look for the 4th one. What if we think we have 4? You can see now that the width, the maximum width of each silhouette is starting to differ, right? So we have a large one, and we have some thinner ones. We continue looking, see how things are starting to break. So this is too many clusters. Some of them are not that tall or extended. And so this silhouette tells me that 6 clusters is not good enough. Okay, so we have to go back and take the silhouette that has the most more or less uniform visualization. So maybe 2, probably 3, and even sometimes 4. So we have to play with that range. Okay. Okay. So let's try another method, the mean shift. I don't have to say how many clusters I want. It will automatically create. Do I have a question? How do we get a plot without assigning it to a plot object first? Assigning it to an object first? You mean defining it? Or I'm not sure. Okay, so that's a Matplotlib question. Okay. Remember, there's more than one way of doing the same. So in k-means. Okay. Well, that goes on. So let's try the mean shift. Mean shift, there's an estimate bandwidth. And so again, let's try Coulomb length and Coulomb depth, and it will compute this bandwidth. And then we will compute the mean shift for that bandwidth, and it's gonna fit the X set. And it's going to create some labels for the model, the mean shift. And then we will have these cluster centers and some labels. And then we execute. And for this variable, the mean shift algorithm tells me that the number of estimated cluster is 3. So what I will do is just plot them. And I have these figures are the center of mass of each cluster. So I have the first cluster in yellow, the second cluster in blue, and the third cluster in pink. Okay, so using mean shift, it tells me that I can only, well, with 3 clusters, I have a good result. I have commented here out a different scenario. What if instead of looking at the Coulomb length and the Coulomb depth, I look at the flipper length versus the mass? I run it again. I'm just changing 2 different variables. That will be a completely different case. And then I will plot them. So if I look at the flipper length and body mass, the mean shift tells me, algorithm tells me that I need 5 clusters instead of 3 on the previous case. And then if I plot them, I have now five clusters, and these are the center of mass of each cluster. So if you're analyzing different variables, you have completely different cases. So it's just, of course, I have 2 different variables. It's a different case. And then the clustering algorithm, like mean shift, tells me that I can split that data set or those 2 variables of original data set into 5 clusters. So that's so every variables you analyze, if you do a different combination, you will get a different result. Okay, so I will leave it like that. Okay. The next one is the hierarchical clustering, so a hierarchy. And I'm going to import agglomerative clustering. And I'm going to again do the Kuhlmann length versus the Kuhlmann depth. And the silhouette coefficient is minus 0.046. Okay, and then I will plot up to 3 levels, 6 clusters. Okay, and plot. Okay, so this is the hierarchical clustering, and I'm using the 6 labels. And then I want to create the dendrogram. So I just create the dendrogram for the hierarchy. Well, I'm just adapting the code to the penguin's Kuhlmann length and Kuhlmann depth. And then this will be the dendrogram. Let me increase. Come on, less. Yeah, so this is the way I would cluster with 3 clusters the Kuhlmann depth versus the Kuhlmann length. And so I have 3 levels. So this is the first level, second level, and third level, and this is the elements of the clustering for every cluster. Okay, so that's another way of visualizing this. Okay, let me go to the next one, which is called DB-scan. It means density-based spatial clustering of applications with noise. And again, the name of the algorithm is DB-scan. We import some metrics, standard scalar, and then there's this parameter epsilon, which is some threshold. And then we're going to fit the penguin's Kuhlmann depth length versus the depth. And then execute. And then it will apply 4 labels. And then we're going to plot. So this is the 4 labels of the clustering of the Kuhlmann depth versus the Kuhlmann length using the DB-scan. So I see 3 clusters. Optics will be related to DB-scan. So it's another algorithm. I will use optics instead of DB-scan because it covers both. So optics, yeah. And the cluster, it will look like this. Okay, and in this case, we have this reachability plot. So we have the first cluster, we have the second cluster, and we have the third cluster. So this is how. And depending on the value of epsilon, this is the result from the optics. Depending on the value of epsilon threshold, this is a DB-scan with 0.5 epsilon, and this is DB-scan with epsilon equal to 2. And you can see we have 3 clusters here, more or less. Okay, and that's okay, and that's a very fast review of the different clustering algorithms. And as I was saying, you can always use 2 or 3 methods to see how your data can be clustered. And also using like besides the elbow method and the silhouette method, there are some other metrics that you can use. So let's go and look for metrics. Clustering. Yes, cluster. Let's go back. There's some metrics we can always uh, take advantage of, and see if I can comment very fast. No, this is performance. Yes. Where is the silhouette? There's another metrics, Jacquard distance, I think. No, well, I don't find them. Okay, so they all say different number, but you will have, then what you can do is take a vote. You have two algorithms or three algorithms saying what's the optimum number of clusters, and then you will have your answer. Um, and and your result will depend on which variables you are playing with. So that will be the answer. So you can use the silhouette. You can use, there's another one called Jacquard metric index. So to compare the similarity between different or diversity between these different sample sets, and basically it's a measure of the intersection between two data sets. So it's another metric you can use. So that's another one besides the silhouette method. Okay. Any more questions? Okay, so stop sharing. If you have any more questions, please let me know. You have a Jupyter Notebook working, and also you can look for more examples in the internet or even in the documentation for scikit-learn. So it's a good source, and also you have to justify your answer, so you have to do it with different methods, and then maybe use additional metrics in order to justify your results.